Hi everyone. So today we're going to talk about integration by U-substitution. At this point in your calculus career, you should only know how to integrate when the integrand is a known derivative of some other expression. So for example, if we have the integral of secant squared x dx, we know that this is equal to tangent of x, and then because it's an indefinite integral, we add plus c. Okay, so we can integrate anything where we know that this integrand is the derivative of some other expression. Okay, so basically we've learned all these derivatives, and then if you just go in the opposite direction, you get the antiderivative. So anything in this table, in this integration table, we can just use the formula. So whenever the integrand matches anything you see in this table, so for example, we use this, this one here, secant squared u du. It doesn't matter if it's u du or x dx. That's irrelevant. But so anything we see here, we can just take the antiderivative and we're done. But what if we have an integral where the integrand, the part in between the integration symbol and the dx or the du or whatever, is not something that's in this table, is not a known derivative? Well, then we have a plethora of methods that we can use to evaluate the integral. And one of the first ones that you would learn in a typical calculus course is integration by U-substitution. So remember, this is just one of many methods of integration. Not every integral can be evaluated with U-substitution, but in this video, we're going to go through how U-substitution works and do some simple examples with integrals where they actually can be solved by U-substitution. So let's go ahead and just look at the first example. Evaluate the integral. So we have the integral of 4x cubed secant squared x to the fourth dx. And if we go to this integration table, you're not going to find that specific integrand anywhere in this table. So we can't just use the known derivative, take the antiderivative, and we're done. We have to use an alternate method. In this case, we're going to use the method of U-substitution. So what we're going to do for U-substitution is we're going to create a new variable u. We're going to say let u equal, and we're going to set it equal to some expression with x. So looking at this integrand, we have 4x cubed secant squared x to the fourth. So we have lots of choices for an expression with x. U could be x cubed, it could be 4x cubed, it could be x to the fourth, it could be secant x to the fourth, it could be secant squared x to the fourth, it could be the entire thing, 4x cubed secant squared x to the fourth. There's tons of different ways to break up that integrand into some expression with x. So as we go along, we're going to get into more detail about how to choose the correct u. But for this first example, just to keep it simple, I'm just going to tell you that we're going to let u equal x to the fourth. Okay, so that's step one, assuming we assign the correct expression to our u. Step two is we're going to take this equation that we just made, u equals x to the fourth, and we're going to differentiate both sides with respect to x. So dx of u equals d dx of x to the fourth. The derivative of u with respect to x is just du dx. And the derivative, excuse me, of x to the fourth with respect to x is 4x cubed using the power rule. Okay. One last step, we are going to separate the differentials, the du and the dx, by multiplying both sides by dx. So we're solving for du basically. So du equals 4x cubed dx. Now, the goal here is to have some u expression based on this assignment of the u variable. Okay, so if u is x to the fourth, we can write the secant squared x to the fourth as secant squared of u. Okay, that's our u expression. Now the goal of U-substitution, in order to determine if this is going to work or not, we need all the outside stuff. So everything outside of this secant squared x to the fourth, which would be this 4x cubed and this dx, we need all of that to line up with the du so that we can make a du substitution. Well, if we look, du is 4x cubed dx. So for this example, everything lines up perfectly. So we have exactly what we want. Now let's go ahead and make the substitutions. Okay, so we have the integral secant squared u and this 4x cubed dx together, they become just du. So now we have the integral of secant squared u du, and this is a known derivative of tangent, so the antiderivative will be tangent. We just saw that in the previous example. We saw it in the table. So this is going to evaluate to tangent of u plus c. Okay, now, our original problem was in terms of x, so we need our final solution to be in terms of x. So the last thing we do is we go back to our definition of u, and we're going to substitute x to the fourth back in for u. So final answer here is going to be tangent of x to the fourth plus c. Okay, let's go to the next example. We have the integral of 1 over 5x plus 2 dx. So we have fewer choices for u here. I only see two expressions with x. I see a 5x and a 5x plus 2. Well, we're going to see in the next slide about how to choose the u. When we have a rational expression with the numerator and denominator, it's pretty common for the u to be either the entire numerator or the entire denominator. Okay, so let's use that logic and set u not just to 5x, but the entire denominator of 5x plus 2. And we're going to do a little bit of a shortcut here. So when we take the derivative, I'm just going to go straight to du dx equals the derivative of 5x plus 2 with respect to x is 5. And then don't forget to multiply both sides by dx. du equals 5. And once you get used to this process here, you can pretty much skip from this one to this one, which we'll start doing in future examples. Okay, let's start to rewrite our integral now. So now we have the integral of 1 over u. So this 1 over 5x plus 2 became 1 over u. So what is the outside stuff? We only have dx on the outside of our u expression. And here we have 5 dx, so we're missing a 5. So somehow we need to get a 5 in this integrand in order to evaluate this and use U-substitution. Now there's two ways of doing this. I'm going to show you both ways, and I'm going to let you choose which way makes the most sense to you, which way do you think is easier, and then you can go ahead and use that way for every problem from now on. But to start, I'm going to show you both ways. Okay. The first way comes from the idea that we can manipulate any coefficients in any integral. So if let's say I have the integral of 3 sine 2x. But in order to evaluate this integral, dx here, I don't want it to be 3 sine 2x. I want it to be 2 sine 2x. Well, that's no problem because when we have a constant in the integrand, we can pull it out. And also, any number could be written as any other number multiplied by some other number. What do I mean by that? Well, if I want to turn a 3 into 2, I could write this as 2 times 3/2 sine 2x. Okay, so 3 is the same as 2 times 3 over 2. The 2's cancel, we get 3. I haven't changed anything. Now all I need to do, since 3/2 is a constant, I can pull it to the outside of the integral. And now we get 3/2 times the integral of 2 sine 2x dx. And now this is what we wanted. This is actually going to work very easy for U-substitution. For U-substitution for integration, it's basically the integration counterpart to the chain rule of differentiation. So you can imagine if you took the derivative of, let's see, negative cos 2x, you would get 2 sine 2x, okay, using the chain rule. So this integral here will evaluate to negative cos 2x. And so that's why we wanted this to be a 2 and not a 3. But anyway, the whole point of this is you can manipulate to get whatever constant you want by making two numbers multiplied together, one of those being the number you want, and the other one you just pull to the outside of the integral. Okay, so 5 we can write as, this is, it just says 1 over u, but that's the same as 1 times 1 over u, right? Anything is the same as itself times 1. So we want to change a 1 into a 5. How do we do that? Well, 1 is equal to 5 times 1/5. Okay, so we're going to change this to 5 times 1/5. And the 5 we're going to leave inside because we need it to align with the definition of du. And the 1/5 we don't need, so that's what we're going to pull to the outside. 1/5 integral of 5 times 1 over u dx. And now you can see the du aligns perfectly. All the outside stuff, 5 dx. The outside stuff, 5 dx. So we can just change that to du. So let's go ahead and finish this up. We now have 1/5 the integral 1 over u du, and this becomes 1/5 ln absolute value of u plus c. Finally, substitute the 5x plus 2 back in for u, and we get 1/5 ln absolute value 5x plus 2 plus c. That's our final answer. Okay, that's one way of doing it. That's actually my preferred way. But most students and most teachers are actually going to teach you this second way. And so I'm going to show you how this way is done. And then from now on, we're going to be using this second way for every problem, just because that's the most common in the classroom, I believe. Okay, the second way is to go back to our du definition. Du equals 5 dx, and take it one step further and actually solve for dx. So divide both sides by 5, dx equals 1/5 du. And now we can substitute for this dx directly. Okay, so we're going to have the integral. Once again, this part just becomes 1 over u. Just like before. Now this time we only need to substitute for the dx. We don't need everything to line up perfectly. Dx equals 1/5 du. And now we can just pull the 1/5 outside of the integration symbol. And now this step is the exact same as this step here. And so from there, these final two steps will be exactly the same, and we'll end up with exactly the same answer. Okay, so to recap, the first method, we manipulate the coefficient in order to get everything to line up with the du the way we want. And then the second method is, instead of just solving for du, we take it one step further and solve for dx, and then just substitute. And then once we substitute, we just manipulate what we have here. And we'll be using the second method from now on. Okay, before we move to the next example, let's talk about choosing the right u. So if you have a rational function, the correct u is often the entire numerator or the entire denominator. If you have a function that takes an argument, such as a trig function, a logarithm, or a radical, the correct u is often the entire argument of that function. So for example, if you had like a sine of x squared plus 2 in parentheses, the u might very well be the x squared plus 2. Or if you have the square root of 2x minus 5, then u might be 2x minus 5. If you have an exponential raised to a power that is an expression of x, the correct u is often that expression. If you have e to the power sine x, maybe your u should be sine x. But once again, these are just all rough guides. I'm saying maybe a lot. There could be some trial and error. Maybe you choose a u and try to work out the problem and it doesn't work. Then you have to go back and choose a different u. There's also, most teachers aren't going to do this to you. They may. But there's plenty of integrals that cannot be evaluated with U-substitution, and you would have to use a different method. So these aren't always going to work, is my point. Okay, so the most important thing to remember is that you must choose a u so that all this stuff outside the u expression aligns with the du. For example, if we have the integral of cosine x e to the sine x dx, let's go back to this. If you have an exponential raised to a power that is an expression of x, the correct u is often that expression. So here we have an exponential raised to sine x. So let's try u equals sine x. And then let's see if we can skip the intermediate steps this time and go directly to the du. Du would be cos x. And a lot of my students do it this way and then they forget the dx. Don't forget the dx, very important. So does that align with the outside stuff? Well, here's our u expression. This will become e to the u. So the outside stuff is cos x dx. And yes, it aligns perfectly. So that means we did, in fact, choose the correct u. If that stuff doesn't line up, that means you didn't choose the correct u, or, and this is why it gets a little bit complicated, sometimes not everything will line up and the problem will still work. We just have to use kind of a more advanced technique, which I'm going to show you in the next video. The next video will be U-substitution with some more advanced problems using more advanced technique. Okay, and one last thing I want to say that's not on this slide. If you have two polynomials in your integrand, so let's say you have the integral of 4x cubed plus 2 over 3x squared. So we have two polynomials in the integrand. We have 4x cubed plus 2 and we have 3x squared. Whenever you have this situation, the correct u is very often the polynomial with the higher degree. And I should say, you have two polynomials here, and they differ by 1 degree. So this is degree 3, this is degree 2. They differ by 1 degree. In that specific case, the correct u is often the entire polynomial with the higher degree. So in this case, u would be 4x cubed plus 2. And the reason for that is because then the du has 1 degree less, because when you take the derivative of a polynomial, you end up with a polynomial of 1 degree less. 12x squared, and then this 12x squared can align with the 3x squared. Remember, we can manipulate the constant however we want. This actually, in fact, won't work because it's in the denominator of a fraction, so I should have actually switched these. But you get the idea. You see how that if you have two polynomials, one is 1 degree higher, if you choose that higher one for the u, when you differentiate it, you're going to get a polynomial 1 degree less, which should align with the other one. And we actually saw that in this first example. So we had a polynomial x to the 4th, we had a polynomial 4x cubed, so we made our u the polynomial with the higher degree, and that way our du ended up aligning with the 4x cubed. So that was one thing missing from this slide that I feel is important. Okay, let's do a few more examples and see if we can get used to choosing the correct u. So here we have an example of what I was just talking about. We have two polynomials, and one is exactly 1 degree higher than the other one. So let's go ahead and try setting the u to be the higher degree polynomial. U equals 4x squared plus 5. And see if we could go directly to the du step. 8x x. Okay, and that aligns with the 24x. Remember, the coefficients don't matter because we can manipulate them. But we have x to the power 1, x to the power 1, so that's good. And let's go ahead and use the second method here, where we take this one step farther and we solve for dx. So dx equals 1 over 8x du. Now let's go ahead and make our substitutions. We have the integral 24x over u squared So that's our u expression, is that u squared. And then the dx is 1 over 8x du. So this dx becomes 1 over 8x du. Okay, the x's cancel. 24 over 8 is the same as 3, and since it's a constant, we can pull that to the outside. So we have 3 times the integral. 1 over u squared, I'm going to go ahead and write as u to the negative 2 du. Now we have something that we can anti-differentiate using the power rule. So we get 3. Add 1, we get negative 1, divide by that. So divide by negative 1 is the same as multiply by negative 1. So we're going to have negative u to the negative 1, which is 1 over u, plus c. And go ahead and multiply that out. We get negative 3 over u. But remember, we want this to be in terms of x, our final answer. So negative 3 over 4x squared plus 5. Plus c. Now, I think this would be a good time to talk about checking our answer. As I'm going through this problem, I think I'm doing everything right, but I'm not totally sure. Did I arrive at the correct answer? So here's how you check. If we take the derivative of this solution, we should end up with the original integrand here. Okay, so let's go ahead and take the derivative. Let's start by rewriting this as negative 3 4x squared plus 5 to the negative 1 plus c. We're going to take the derivative of that with respect to x. So negative 3 is a constant, that just stays in front. Now we use the power rule, so the negative 1 comes in front. And then we have 4x squared plus 5. The negative 2. We subtract 1 from the power. And then, based on the chain rule, we have to multiply by the derivative of the inner function, the derivative of 4x squared plus 5, which would be 8x. And then c is just a constant, so the derivative of the c is just 0, so that just goes away. So let's go ahead and simplify this. The negatives cancel, and 3 times 1 times 8 is 24, so we're going to have 24x. And then since the 4x squared plus 5 is raised to a negative power, we're going to move that to the denominator, and the power will become positive. 4x squared plus 5 squared. Does that match our initial integrand here? Yes, so that's how we know, yes, we did everything correct, and we know that our answer is right. Okay, a couple more quick examples here. Evaluate the integral cosine of 5x over e to the sine 5x dx. Well, let's see. If we make u sine 5x, then the derivative would be 5 cosine 5x, which seems to align with the outside stuff. Let's try that. U equals sine 5x. Now, if you're still confused about how to choose the u, don't worry too much about it. Just take your best guess and try it, and if it doesn't work out, then go back and choose a different u. But let's go ahead and try sine 5x. It seems to match some of the criteria of the tips for choosing the u here. This same one that's underlined. If you have an exponential expression raised to a power that's an expression of x, the correct u is often that expression. We have an exponential raised to some power that's an expression of x, so it's a good choice. Okay, that makes our du the derivative would be cos 5x, and then the chain rule says we have to multiply that by 5, and then don't forget the dx, remember. And we'll take it one step further and solve for dx. So we're going to go ahead and imagine the 5 being in front here. We're going to divide both sides by 5 cos 5x. So 1 over 5 cos 5x. Let's make our substitutions. Here's our u. So in the denominator, we're going to have e to the u. And here's our dx. And I made a mistake over there. That should have said d. Sorry about that. Okay. So we have the integral of cos 5x. And then this became the u, and the dx is going to become all of this. So we're multiplying by 1 over 5 cos 5x du. Okay, the cosine 5x's cancel. And the 1/5 that's left over, we can go ahead and pull that outside the integration symbol since it's just a constant. So now we're left with e to the u in the denominator, which is the same as e to the negative u du. Now, we have a problem here. We still don't have something that we can antidifferentiate. We don't know the antiderivative of e to the negative u. we know the antiderivative of e to the u. So one thing we can do here is another u substitution. Okay, let's think about doing the chain rule in a differentiation problem. Sometimes you have to use the chain rule multiple times, right? Well, if u substitution is the counterpart to the chain rule of differentiation, then it's possible sometimes we'll have to use the u substitution multiple times. Okay? Now, to avoid confusion, since we've already used u, I like to just choose another letter, v. And since all we have is e to the negative u, I'm just going to make v negative u. Okay? Because that will make this expression e to the v, and we know how to anti-differentiate e to the v. Now, dv would be negative du, and du would equal negative dv. Okay, let's make those substitutions. We have 1/5 integral e to the v, and then du is negative dv. Okay, we can pull that negative to the outside. We have negative 1/5 on the outside. So now we have e to the v dv. So the antiderivative of e to the v is just e to the v. Negative 1/5 e to the v, and because it's an indefinite integral, we add plus c. Now, we first have to back substitute for the u. Okay, so v is equal to negative u. So this becomes, it's going to be equal, so I suppose I can just use an equal sign. Negative 1/5 e to the negative u plus c. And then the original u was sine of 5x. So negative 1/5 e to the negative sine 5x plus c. And that's going to be the final answer. And one last thing I'll say about this problem. Just because if the integrand results from differentiating using the chain rule multiple times, it doesn't necessarily mean you have to do a u substitution multiple times in order to integrate. In fact, in this particular problem, if we would have chosen our original u to be negative sine of 5x, then we would have only had to do the u substitution once. Okay, so there's times where a u substitution will work and you'll have to do it multiple times. But if you were to choose a better u, or not necessarily better, but a more comprehensive u, a different u, then sometimes it's possible to do it in just a single u substitution, depending on which u you chose. Okay, so that's about as complicated as I want to get in this video, except that so far all the problems have been indefinite integrals. So I just want to do one example using a definite integral, which is actually a lot easier than you might think. One reason is the first few steps are exactly the same. And the second reason is, as long as we change the limits of integration to be in terms of u, so we're going to get into it in a second here, but you see this 1 and this 3, these are x values. X is going from 1 to 3. If once we get our u equation, we change those values to be u values, then we never have to back substitute the x expression. We could just evaluate the definite integral directly with the new u values. Okay, you'll see that as we go through the example. So this is the same example as we had before, just with some limits this time. So we made our u 4x squared plus 5. So our du was 8x dx. And go one step further and solve for x. Dx equals 1 over 8x du. And let's make our substitutions. So we have the integral. I'm going to leave the limits alone for now. We have 24x over u squared times dx, which is this 1 over 8x du. And now let's go ahead and look at the limits of integration. So if x is 1 and u is 4x squared plus 5, just substitute 1 for x, so we get 4 times 1 plus 5, we get 9. And now when when x is 3, 3 squared is 9, 4 times 9 is 36, plus 5 is 41. So when x goes from 1 to 3, u goes from 9 to 41. Okay, so 24x over 8x is just 3, and we can move that to the outside. So we keep going here, and we get 3 times the integral 9 to 41. I'm going to write this as u to the negative 2 du. So that's equal to 3 negative 1 over u. From 9, 1. So we get 3. And then negative 1 over 41 minus negative 1 over 9. I'll just kind of leave it at that and let you, if you want to get a common denominator and simplify the fraction, or if you just want to plug it into the calculator and get a decimal approximation, either way is fine, but we're running kind of long on this video, so I'm just going to leave it here and leave the simplification to you. Okay, so these were the basics of U-substitution, integration by U-substitution, I should say. And we did some simple examples, but there are some more tricky examples, some more advanced techniques that we're going to get into in the next video. So I encourage you to check that one out as well.